We're going to look now at population growth and decay. And keep in mind that growth will be increasing and then decay will be decreasing. We're supposed to be looking at the y-intercept and interpret its meaning and then determine if the city's population is increasing or decreasing. So we have the city function population over time is equal to 4,000 times 1.03 to the t power. It represents the population of Millville as a function of time. So let's go ahead and look at what it would look like on a graph. And I'm just going to graph this on Desmos. So 4,000 times 1.03 to the t power. You can't see anything on this graph. And the number one reason is because you are starting with a population right here of 4,000. That's your y. This number right here is going to tell you where the graph crosses the y-axis. And here it only goes up to 10 on the y-axis. So I need to go to the tools and I need to make my y-axis go up to 4,000. But let's make it a little bit more than that so that we can actually see the graph. And then another thing we're going to do is our x is our time, and it doesn't make sense to have a negative amount of time. So let's go ahead and just change our time, our domain, so that it starts at 0 and then it goes up from there. So you can see now what the graph will look like. It's going to start at 4,000 and then it's going to increase. So if I were to stretch it out over a little bit more time, like 25 years, you could see that it's exponential, it's curved. So let's go ahead and sketch what that graph would look like. It's going to start at 4,000 and then it's going to curve. It's going to go up over time. So we need to answer the question, what's the y-intercept? That's 4,000. And notice that it's this a value in my exponential function. If you remember from previous models, exponential, your a value is your y-intercept. Okay, so our y-intercept is 4,000, so that's the starting population. And then it says to determine if the city's population is increasing or decreasing, and it is increasing. And one thing to keep in mind is that our common ratio is 1.03. So your B value, if that is a number that is greater than 1, then it's going to be an increasing. So this is increasing. So for example, if I were to change my growth factor or my common ratio to a number that's smaller than 1, so like 0.99, now you can see it starts decreasing. Or if it were like 0.50, now it's decreasing really fast. But a number that's bigger than 1, like 1.25, now you can see that it's increasing. Any number bigger than 1 for your B value is going to make your graph or increase. So when we look at number 2, it says the function population over time equals 8,000 times 0.98 to the t power represents the population of Grand City as a function of time. So let's go ahead and graph that one and see what it looks like. So it's time on the x-axis and population on the y-axis. And just like I was showing you with number 1, our y-intercept in this case is 8,000. So that's going to be our y-intercept. So we'll go all the way up to 8,000. And that's the starting population. And what we needed to do is determine, is it going to be increasing or decreasing? I'm predicting that it's going to be decreasing because this number right here, my B value, is less than 1. So it's going to be decreasing. So let's, all right, we should have a graph like this. Let's just double check on Desmos. So we have 8,000 times 0.98 to the t power. And you can see it starts with 8,000. That's our y-intercept. And then over time, it's decreasing. Population is decreasing. You might also notice that the population never actually becomes less than 0. We have this asymptote right here. So our asymptote is just going to be when the population is 0. It's never going to go below this line. We're not going to end up with a negative amount of people.